Well, hello, everybody. This is hss2381 Statistics, and I see that there are no viewers right now. All right. I'm dialing on my other computer so I can start my Twitter and see if there are any real-time questions. So again, my Twitter handle is at Dionandon. Let me put that on the screen for you to see if I can figure that out here. Toolbox. At Dionandon. Here we go. Excellent. So I'm sorry I had to change class today. I couldn't be there in person. My back is killing me. Don't get old, people. Getting old sucks. But today's lecture is the last lecture of the course, I am sorry to say. So Friday's class is canceled. However, having said that, I will set up special office hours sometime in the next couple of weeks for you to come ask me questions before the final exam. In today's class, however, we are going to talk about the final exam and everything we've talked about so far in this class. So let me go and start the slides. Give me a second here. Starting slides. I'm going to share the screen. Okay, sharing the screen. Now, okay, you should see a blank screen right now. It should say loading, and we are sharing. Very good. Okay, give me a second here as I check my Twitter feed here. All right, no one's asked me any questions yet. Again, if you have any questions throughout the ordeal that is this class, feel free to tweet me at Dionandon. 1 second here, let me just present everyone. Very good. Okay, today, first of all, like I said, Friday's class is canceled. Yay, good for you. That's fantastic. You should be sad about that. You should be sad that you'll no longer be exposed to my wisdom and my brilliance. What we've done so far this semester, after the midterm, because remember, your final exam is not based upon anything prior to the midterm. It is not cumulative. We've done the one-way ANOVA, right? You learn how to do that by hand. We haven't done the two-way or the n-way by hand, but you know what those are. We've done the chi-square and McNemar's test. We've done ranked correlation. Remember, prior to the midterm, we did unranked correlation. We did linear regression, and we did a basic sample size calculation. We also learned about the different types of chi-square, the Kruskal-Wallis test, etc., the two-way and the n-way ANOVA, and multiple regression, but I will not be asking you to do those calculations. I'll only ask you to know the theory behind them. So let's go over ANOVA first. ANOVA, of course, stands for Analysis of Variance, and it tests whether the mean of things in different groups are different from one another. So if you have more than one dependent variable, then it's a two-way or n-way. If it's more than two, then it's n-way. So let's go through some examples of this. And remember, in this class, we only learned how to do one-way ANOVA by hand, but I want you to know when we would use two-way and n-way. For example, if we're comparing the mean bacterial count in 4 samples of milk, the number of dependent variables there is 1. That is the 4 samples of milk. So that's a one-way ANOVA. If we're comparing the mean weight of men versus women among Canadians and Americans, well, the independent variable there is weight, but the dependent variables are men and women and Canadians versus Americans. Okay, that's a two-way. And for the third example here, it's the mean price of 6 categories of vegetables in different grocery stores in different countries. So the number of categorical variables there is 3. So that's n-way. Okay, so the dependent variable, again, I always get these two confused. I'm so sorry, and I just got confused again. The dependent variable is the thing that you're computing the mean of. That's always going to be a continuous variable in interval or ratio level. Let me go back 1 second to these examples here, now that I've got it straight in my head. So in the first example, comparing the mean bacterial count in 4 samples of milk, the dependent variable is the bacterial count. The samples of milk are the independent variable. Okay, so the dependent variable is always continuous. The independent variable is always categorical or nominal. It can be ordinal as well, but we tend not to admit that. We have two kinds of variation in ANOVA, you recall. There's between group variation. That's the differences between the different categories we're comparing. And within each category, within each sample of milk, within each factory, within each class, there's also variation. So in ANOVA, we like to compute the F statistic. Oh, I have a question here. Oh, right on. Oh, now someone called I Have a Dream is now following me on Twitter. Well, that's not a question. So in ANOVA, we compute the F statistic, or the F ratio it's called, because the F ratio is just the ratio between the between group variance and the within group variance. We also have degrees of freedom, much like every other test that we perform in this class. We have between groups degrees of freedom and within groups degrees of freedom. And you see here on the right side of the screen what the definitions of those degrees of freedoms are. For the between group, it's k minus 1, where k is the number of groups, number of categories, right? And within group is n minus k, where n is the number of subjects. So how do we do this? Well, step 1 involves calculating the sums of squares. We do it within and between. Remember how that looks? So then we use the sum of squares and our degrees of freedom to compute our F statistic, given by the formula in blue there. We have null and alternative hypotheses in ANOVA. What's the null hypothesis? It's that the means of the various categories we're comparing are equivalent. And what's the alternative hypothesis? Is that they're not equivalent. We don't know which one is different or all three are different. It's just that they are not all three or all of them the same. Moving on to the chi-square. Yes, I'm moving very fast because I'm still in a lot of pain here, and it's all review. This is the formula for the chi-square. Chi-square we use when we're comparing whether or not two categorical variables are associated with each other. And we compute the chi-square by computing the expected values in our various cells and comparing them to the observed values, which is our data. So again, the chi-square tests whether or not two categorical or nominal variables have a relationship with one another. Some people use it for ordinal variables also. So the example we did in class involving patient satisfaction surveys, I think, was done with an ordinal variable. It's possible, it's just not ideal. So we have two other kinds of similar chi-square kinds of tests. There's the Mann-Whitney-U test and the Kruskal-Wallis test. And we can use those when we have ordinal measures. If there are two groups, we use a Mann-Whitney-U test, or three or more groups, a Kruskal-Wallis test. And again, that's when we have ordinal measures. In practice, to be honest, a chi-square often gives the same results, so we tend not to be too picky at times. Like everything else, the chi-square has a null and alternative hypothesis. The chi-square null hypothesis is that the two categorical variables are independent, which also means that they're unrelated, or the proportions between the two groups are equal. The alternative is that they're not independent, or they are related. How do we do it? Well, we create a contingency table or a crosstab table. We have our observed values, which is the data that is given to you, and we compute the expected values. How do we compute expected values? We multiply the marginals. Remember what the marginals are. The marginals are the values of the totals on the ends of your crosstab table, and we divide each by the total number of subjects. And that gives us our expected values. We have to compute a degrees of freedom as well. So before we compare our chi-square statistic, we have to check that assumptions have been satisfied. The assumptions of the chi-square test are that the observations have been sampled from randomly from a population. Each observation is independent, meaning that as you collect your data, the next value does not depend upon a current value. Each cell in the table must have an expected frequency greater than 0. The expected frequency, again, is the number that you compute. That marginals multiplied by each other divided by the total, that's expected. It can't be 0. And the observed frequency, that's your data, must be at least 5. Again, the textbook says 10, but I go with 5, so you're going to go with 5. Okay, and those last two are really the two most common assumptions that we check for. Again, this is the formula for the chi-square, so you can plug that in and can get your chi-square statistic. And this is the formula for degrees of freedom. So the number of rows, minus 1, multiplied by the number of columns, minus 1. The steps of a chi-square. First, as always, we state our null hypothesis, which is that the two variables are not related. Second, we create our crosstab table. Then we check our assumptions. Remember, the assumptions were mostly about the expected observed frequencies. And we compute our test statistic and our degrees of freedom. There's someone knocking on my door right now. I'm going to ignore them. And then we compute our chi-square, look up the value in the back of the book, and see if their number is bigger than our number. Pause this for 1 second. I'll be right back. 1 second. Okay, sorry about that. That was awkward. So someone knocks on my door as I'm doing a video conference here, and there's a delivery guy, and he needs me to sign for something and then pay $4 in delivery charges, and that takes forever. And then he wants me to talk about the sitar that I have in my living room and whether or not. Anyway, long story. I'm back now, and hopefully you haven't gone away. You're still here. Good. So these are the steps that we do for the chi-square. And after we compare our chi-square value at the back of the book, we assess the null hypothesis. Always answer the question. Next, we did ranked correlation. Remember, ranked correlation is different from our regular correlation because ranked correlation looks at the order in which our things occur and not the actual values of them. And our ranked correlation tests whether two ordinal variables are related or one ordinal and one a non-ordinal variable. We computed Spearman's ranked correlation. It's a form of Pearson's. Pearson's is what we did before the midterm. And it uses, again, interval ratio data. Remember, Pearson's row tests for a linear relationship. That's what we did before the midterm. Spearman's row tests for a monotonic relationship. Remember, a linear relationship is a straight line. Monotonic means it goes up together, it goes down together. May not be a straight line. It might be some wiggly snake-like thing. So here's some examples of ranked or unranked relationships. Correlating people's preference in ice cream flavors with calorie count. That's ranked. Anytime we have preference, that's ranking. Children's age and height, that's unranked because you're looking at the pure numbers of age and height. Property tax with number of rooms in a house. Either one works there. And the reason either one works is that rooms in a house can be argued to be ordinal. However, because the distance between 1 and 2 and 2 and 3 and 3 and 4 are the same, it can be treated continuously. So either ranked or unranked work here. And lastly, correlating the favorite world cities with their average temperatures. Anytime you have preferences or favorites, we have automatic rankings. If there's ranking, we use ranked correlations. This is the formula for Spearman's ranked correlation. Remember, we have to create our spreadsheet and compute the differences and square them and add them all up and all that wonderful stuff. We also have a degrees of freedom. So for both Pearson's and Spearman's ranked correlation coefficients, the degrees of freedom is the number of subjects minus 2. So From there, we went on to linear regression, which is the good stuff, the stuff that you might actually find useful in your life. Linear regression is when we attempt to model a linear relationship. A linear relationship is one in which the exponent is just 1 between two continuous variables. Okay, we usually do this to make predictions. For example, predicting how you will do on your final based upon how you did on the midterm. So with linear regression, we have a bunch of values for x, and we try to figure out the best intercept and the best slope, such that this formula, this equation, this sentence, y equals alpha plus beta x, has the closest possible fit. And the technique for the closest possible fit is something that we call the ordinary least squares method. There are different ways of computing a best fit, but this is the method that we learned, the ordinary least squares method. Okay. So remember, when we finally make our equation, the y, in this case I write it as y prime, is a prediction now. Based upon your values of x, we plug it into the equation and predict a value for y. So on an exam, I may ask you to create a linear regression equation, then give you values for x and ask you to predict a certain outcome. So b, or beta, is the slope. Back in high school, you call that m. We also call this the regression coefficient. And a, or alpha, back in high school, you would call this b, is the y-intercept. As I mentioned, we use the ordinary least squares method, which is a way to minimize the vertical distance between each of the points and the line that we're plotting. It's not the only way of doing it. We could have minimized the horizontal distance or the orthogonal distance, but we're choosing to minimize the vertical distance. Now, technically, your linear model is in fact y equals a plus bx, or alpha plus beta x, plus an error. The error is not constant. The error changes for every point. And that error is the difference between what the model predicts and what the actual point says. We call the error also a residual. Okay, so our residual is defined as the actual point minus the predicted point on the y-axis. We can compute a standard error of the estimate. And remember, standard error is the error of this theoretical distribution. And that is the sum of all the squares of the residuals divided by n minus 2 under the root sign. How is that useful? It's useful because then we can use that now to test whether or not our slope is equivalent to 0. Why we want to do that? Well, we want to do that because it can be argued that a 0 slope is a null hypothesis situation, and a non-zero slope is an alternative hypothesis situation. So to compute whether or not our slope is statistically equal to 0, we have to compute a t-value. The t-statistic in this case is going to be the slope that you compute, the beta, divided by that standard error that we just looked at over here, this standard error, using a degrees of freedom of the number of points minus 2. We look that number up in the back of the book. If the back of the book is bigger than yours, then we cannot reject the null, and we know that the slope is equal to 0. There is a relationship between linear regression and correlation based upon this equation here. So this equation allows you to compute Pearson's row, not Spearman's, Pearson's row from the values of the residuals in your linear regression. Then we talked about multiple regression. Multiple regression is like simple linear regression, except we have more than one predictor variables. In many ways, the betas, the slopes, are like weights, right? How much each of these factors is weighted to produce an estimate of the thing that you're trying to predict. An example we worked out in class was trying to predict how long someone would stay in prison based upon a combination of their attitude score and their height and all kinds of other things. So much like linear regression has the R, which is the regression coefficient, multiple regression has the multiple correlation coefficient, capital R. And capital R squared is the percentage of variation in our outcome variable that's explained by the soup of predictor variables. Capital R ranges from 0 to 1. Remember, small r ranged from -1 to +1. There are no negative values in capital R. Then we talked about sample size calculation. right? So sample size calculation is an attempt to know about statistical power, the power to detect an effect. If that effect is real, do you have enough people in your sample to detect that reality? And we landed upon two equations. The first one is n equals 8 sigma squared over delta squared, where sigma squared is our variance and delta squared is the square of the effect size. This equation only works when the power is set to 80%, which is also our beta, right? Power is beta, or 1 minus beta, and our alpha is set to 0.05. Now, in every case that I give you, that's going to be true because I didn't teach you any other sample size equations. So pretty much it's always going to be the case that the power is 80% and alpha is 0.05. So if that's the case, then for a one group study, meaning we're seeing if the pill changes your reaction to something from one level to another level in one given group, this equation works. 8 times the variance divided by the square of the effect size will give you the number of people needed. Remember, you always round up from a decimal because you can't have 11.1 people in your study. It has to be 12. No such thing as 0.1 people. You get the sigma squared from pilot studies or from literature. And the delta is going to be, again, the effect size or the thing you're trying to measure, the width, the intensity, the breadth, the size of the thing you're trying to measure. In class, we worked through the example of 10 millimeters of mercury as the effect size we're trying to measure. The more sample, the smaller effect size we can measure. Now, an asshole professor like me might ask you questions like, if you have 100 people and the variance of the variable you're looking for is this, what's the smallest effect size you can measure? In which case, you'll have to solve for delta. That's the kind of thing I would ask. For a two-group study, there's a different formula, and that formula is n is 16 sigma squared divided by delta squared. Notice it's 16, not 8, and this is n per group. If you have two groups, you have to multiply by 2. So in essence, the two-group study is 4 times bigger than the one-group study because the 8 goes to 16, and this is per group. So do not get these two formulas confused and practice on both of them. So one of the interesting things I wanted from this class for you was to figure out when to use certain tests and when not to. So let's go through some examples. If you're comparing the mean IQ of men versus women among nursing students versus HSS students, well, what test do we use? We use a two-way ANOVA. Why? Because we have 2 categorical variables, gender and type of students, nursing versus HSS. It's one only dependent variable, that's mean IQ. So that's going to be a two-way ANOVA. Two-way because there are 2 categorical variables here. If we are studying the mean blood pressure between 5 ethnicities, Native, Caucasian, East Asian, South Asian, African, that's a one-way ANOVA. It looks like it should be like an n-way, but it's only one way because there's only one categorical variable here, ethnicities. It happens to have 5 levels, but it's only one variable. That's a one-way ANOVA. If we are predicting the final weight loss of the contestants of season 11 of The Biggest Loser based upon their starting weights by looking at the experiences of season 10 contestants, that's a classic linear regression because we're only looking at one predictor variable. That's the starting weight. So again, the outcome variable here is the final weight, and the predictor variable is the starting weight. If I were trying to look for an association between final weight and starting weight, would I still use linear regression? Probably not. I would probably use a basic correlation there because an association is not a prediction. The word prediction here, predict, tells me I'm going to have to regress. And this is going to be simple linear regression. So is there a relationship between which faculty the students are enrolled in and which means of transportation they use? So the way you look at these kinds of questions is to first ask yourself, what kinds of variables are these? What are the levels of measurement? Well, faculty is a categorical measurement, a nominal variable, and means of transportation is also a nominal variable. If we have an association between 2 nominal variables, that's a chi-square, usually. Predicting the sex ratio of the nation of Bangladesh in 2050 based upon values of total base population each year of the past decade. Okay, the word prediction is there, so right away you know it's going to be a regression. We use regression to predict things. You've only learned about linear regression and multiple linear regression, so it's going to be one of those two. Which one it's going to be? Well, our outcome variable here is sex ratio, but the predictor variables are one or more than one. Well, there's total base population in year 1, year 2, year 3, and up to year 10 of the past decade. So there are 10 predictor variables. Because we have more than one predictor variable, it's going to be a multiple regression. Is there a relationship between the number of hours students spend watching TV and the relative standing in stats class? Well, the key there is relative standing. Relative standing means rank, right? Ordinal variables. So we're associating something with an ordinal variable. That's going to be a ranked correlation. Now, let's talk about the final exam, which is why you all turned in. The final exam is Wednesday, December 18th. That is a Wednesday, right? Hope so. 9:30 to 12:30 in a horrible, horrible room, site G0103. In the midterm, you can bring any kind of calculator you want, and make sure you bring one that works. Every year there's always somebody whose calculator doesn't work and they freak out and they want to use their phone and they want to go to the mall and buy a new one. Check your calculator, right? And your cheat sheet. So your cheat sheet, again, is 1 page, 8.5 by 11, double-sided. You can put anything on there you want. Anything you want. You will not need to put on stats tables, like tables from the back of the book. I will give you the relevant ones. You may want to put formulas on there. You may want to put examples on there. You may want to put inspirational phrases from your mother, any number of things. But again, anything goes on the cheat sheet. As you know, it may not help you. What's important is what you know, not what you write down. So what's on the final? First thing is that last year's final had 70 questions, 70. And of those 70, 28 were computational questions. The rest were theory questions. It's all multiple choice. There's no, I'm not marking your handwritten computations. It's all multiple choice. This year, I think I'm going to knock off 5 questions, make it a little easier for you, because last year people found it a bit trying to get 70 done. So I'll bring it down to 65. Yay, you're welcome. And right, so what's on the exam? Well, everything we've learned since the midterm. We've learned one-way ANOVA, we've learned chi-square and McNemar's test, we've learned Spearman's row, linear regression, and sample size. These are the computations that we learned. On the blue text under there it says calculation questions are similar to second day analysis assignment. That's from last year. You didn't have a second day analysis assignment, so you have nothing to compare it to. I have a question. And I have a dream is following me, and I have a dream actually is a student in this class. Well, that's great. And 18th is a Friday. Oh, in that case, the exam is Friday the 18th. Well, that's useful. Let me check on that. See, I have a dream as a student. I thought I have a dream was following me because I'm inspirational and they dream about being me. Yes, that's correct. Friday the 18th. I'm sorry about that. So that slide is correct. It's Friday the 18th. What have we learned since the midterm? Well, the theory stuff, everything we've learned, plus 3 things from the first half of the class. The 3 things you must understand from the first half of the class are the differences between type 1 and type 2 error, alpha and beta, the difference between a null and alternative hypothesis, and how to use p-values, right? And by how to use, I mean how to interpret them. So that's pretty straightforward. The theory questions are very similar to the midterm, so the way I phrase them and so forth, because to be frank, I steal them from the textbook manufacturer, so it's their phraseology. Format, it's all multiple choice. I say half computations, about 28 computations, right, out of 65, and half theory. What to bring? Bring your cheat sheet, bring your calculator. I will not provide equations, so you'll have to bring those yourself. You don't need the tables again. You don't need significant levels, all that stuff. And there you have it. Like I said, we are going to have special office hours before the exam, and I'll let you know what that looks like. And here we go. I'm back on here. We have 23 live viewers, and no one's asking me questions. I guess I was crystal clear, even though I took a break to answer the door. Curious. All right. Well, hey, there you have it. That was quick and dirty. Half an hour's worth of your time. Hopefully nobody had to come in to class to watch this, and you all stayed home. As for me, I'm about to take some painkillers and have wacky dreams. So see you, if not in my office hours, then on exam time. Remember, Friday, no class. Bye-bye.